Welcome everyone. We are Team TriForce Analytica. We are Elijah, Henley, and Magnus, students in Master Degree in Data Science program. Our project title is Leveraging Machine Learning for Advanced Crime Prediction in Los Angeles. Today we're presenting Chapter 3, the methodology. In our overview of the first two chapters, we examine the urgent need for proactive, data-driven policing in Los Angeles against rising crime rate. We review over 40 references from 1990 to 2024 for our literature review. This slide is the map of our presentation for the methodology chapter. Our journey starts from the population in Los Angeles, our data source, and the feature in our data sets. We will present how we prepare the two data sets and how we clean and merge them. And we will present the overview of new dataset after merging and cleaning it, and what's inside it. Last but not least, our algorithm. We are going to explain which feature was picked and why, and what algorithm will be applied. Los Angeles City has nearly 4 million residents, and it has a high rate of crime. Our analysis relies on two main open data sources from 2010 to 2023. The first data source is from LAPD. The crime data contains 28 columns with over 2.8 million rows. Through our first look in the data, we found our crime data that the number of crimes is spread out evenly across different areas. Most victims are in the middle age, but there are some under 0 and some victims are very old. Crime Code 1 is the most severe type of crime and had the highest record compared to Crime Code 2, 3, and 4. The second data source is from the Weather Underground with 5,113 rows and 17 features. The data distribution indicates a range of weather conditions. The temperature is generally moderate with a normal distribution. The dew point and humidity level show a rise skew. The wind speed had some outlier, indicate some high winds, may be due to extreme weather event. As part of our data preparation, we standardize naming by adding underscore to all column names and spaces. As we can see in the first column in the graph, our first merge is the crime and the crime data set from 2010, 2019, and 2020 through 2023. We got 2.8 million rows and 28 features. After that, we execute the inner join crime and weather by date occurrence. So all rows from the crime dataset got exact weather data on exact date. For example, if there are 3 crimes on January 1st, 2023, those rows will get exact weather data. The merging of crime and weather dataset from 2010 through 2023 provided 2.8 million rows and 44 columns. Next, I will pass it to Magnus to talk more detail about new dataset.
So hello everyone and thank you, Hengley. Diving deep into our combined data set, we noticed that 26 variables have missing values, the most prominent of which are on the right-hand side of the screen. We also have outliers like maximum temperature of 162 degrees Fahrenheit, wind speed of over 800 miles per hour, victim age of over 100 years old. We have negative age values, amongst others. It becomes apparent that our combined data set must be cleaned up. Some variables will not be relevant to our predictive models and thus will have to be dropped. There are other issues in this combined data set which must be treated for data accuracy and quality checks. To validate our data, we shall employ data cleaning techniques like imputing values, dropping rows or variables altogether. Crime code 2, 3, and 4 have over 90% missing values, and as a result, they are dropped. The same thing happens with cross street, which has over 83% missing values. They are dropped as well. We created a new feature called weapon reported with binary values 0 and 1, where 0 represents no weapon was reported and 1 represents a weapon was reported. As a result, we had to remove both weapon use code and weapons description. Similarly, a combination of latitude and longitude with 0 value indicate null data. So we have to remove them. There are 1,907 records. We imputed median values for victim age, total precipitation, and other missing weather records. And then for victim descent and sex, we replaced the missing values with unknown. Now, due to the nature of our data with distinct values or categories which run into tens, hundreds, and sometimes thousands, we employ feature engineering techniques to create new variables and reduce the categories of some others. Crime code, for example, is reduced from 144 categories to 8 to help predict the categories of crime better and to avoid overfitting. Victim descent with 19 categories is re-engineered into region ethnic origin of 6 categories. Data code creates date, day of the week, month, and year variables, amongst others. Now over to Elijah for details on our variable selection and research hypothesis. Thank you.
Good evening, everyone. So to support our research hypothesis 1 and 2, which are determining if victim demographics and weather impact types of crime in Los Angeles, we built several models after data cleaning and feature engineering. These models include ones that are useful in classification problems such as these, which are logistic regression, support vector machines, XGBoost, random forest, k-nearest neighbor, and naive Bayes. To determine demographic and weather variables have an impact on crime, the course of action we are taking is to build each model both with and without these variables and determine the difference in model performance. We can then prove or disprove each hypothesis if model performance is not affected when the separate models are built. Here we have listed the target variable that we created during the feature engineering portion of the presentation, as well as the predictor variables that were either native to the dataset or engineered by us. We've determined that these variables are the most likely to give us good models based on correlation matrices and testing some previous modeling. Many variables of the dataset are removed as they create multi-collinearity issues or they are irrelevant. So we're taking a similar approach to answer our research hypothesis question 3, which is, can we predict future crime hotspots in Los Angeles? So to do this, we'll have to create a different approach to help format the problem to use neural networks. In particular, based on research during our literature review, a common approach appeared to be splitting up the different areas in the region and looking at the number of crimes to predict future amounts. We see some seasonality in the data and some crime surges in 2011 and 2023 that we are currently investigating, as well as looking for specific patterns of seasonality. We've also seen a large dip in crimes during the COVID years. So this study makes use of more variables to include area and more time and date granularity to help time series neural networks such as LSTM, RNN, and ARIMA train more efficiently. We are starting to build basic singular networks and continuing to increase network complexity to make better predictions. So to achieve all these goals, Python is the main tool that we're using along with the support of Jupyter Notebooks and Google Colab. Additional modules make the machine learning models and neural network frameworks easy to implement and adapt. Specifically, scikit-learn, which gives us access to all the classification algorithms we are testing and allows us to tune their hyperparameters. TensorFlow provides us the same functionality on the neural network side with the overlay API, Keras, to simplify some of its features. Each algorithm and neural network has a variety of different tunable hyperparameters, and an effective approach that we're implementing is to utilize another Python module known as Grid Search CV, which allows for the creation of dictionaries that will iterate model building and different hyperparameters and print the optimal settings for each model. We plan to use these tools to help us build the most effective models to answer our research hypothesis questions. So to summarize our methodology section, this was a very robust and challenging section that required a very comprehensive analysis of the data and proper processing to make sure data integrity remained in place. Several data issues were discovered and removed, and in order to make sensible use of classification algorithms, the target variable was grouped into broader categories to help with predictions. Other features were also developed to reduce the high level dimensionality present in the data set before resorting to more abstracted ways of making predictive models, such as principal component analysis. A lot of these techniques were necessary just to allow models to train in a reasonable time frame. Some models did not even train over the course of a few days, even when using a Tesla A100 GPU, which are extremely fast, so we had to adjust our approach a bit. This might sacrifice a little bit of accuracy for the sake of practicality. We are now in the process of making model adjustments to make them as accurate as possible, as well as adding and removing the predictive variables needed to support our research questions. In the next chapter, we will go into great detail on our results and if we were able to prove or disprove each of our hypotheses.